Hello, everyone. I'm Kat Massey, the Director of the Ambient Air Division at Apex Instruments. Thanks so much for joining our webinar today, where I'll be discussing what we do to ensure quality assurance and discuss some of our calibration options related to our multi-pollutant air quality monitoring system that's manufactured by Kunak. Before we get into things, I want to just share a little bit about Apex Instruments for those who might not be super familiar with our company. We've been around since the late 1980s and are headquartered in North Carolina, not too far from Raleigh. And we're experts in manufacturing and selling different air quality monitoring equipment. Initially, that really focused in on emission stack testing equipment, but now we've expanded into ambient air monitoring markets, as well as we provide training related to emissions work, and we also build out custom mobile laboratories and trailers. Now, the Ambient Air Division, we represent two different product lines. On the left is our customizable multi-pollutant sensor system manufactured by Kunak, which is the topic or will be discussed today during the webinar. And then we also have field deployable volatile organic compound analyzer that allows you to speciate VOCs in near real time. And happy to talk about that if you guys have questions in the future. So today's webinar will cover some background information about these Apex Air products, and then we'll discuss how we embed quality assurance into multiple phases of operation, and I'll discuss our different calibration options for these systems. So a quick bit of background about the Apex Air products. So these devices are meant to be really in between a reference quality station and lower cost air quality sensors. So we're aiming to be professional grade sensors that provide accurate data, can analyze multiple pollutants simultaneously, are quite cost effective, enable higher spatial resolution, and we're ongoing and we're continuing to get additional certifications on these products. Now, part of the air quality suite of offerings, we have two different sensor systems. On the far left is the Apex Air Pro, and this device can monitor up to 5 gases and PM simultaneously. Then we have the Apex Air Lite, which can monitor 2 gases plus PM simultaneously. And this technology is really hedged upon the unique cartridge design for the smart gas sensors. So we have 12 different pollutants available, and these are plug and play. So you just pop them into the different slots for the 2 different sensor systems. Then all of this is tied into a cloud-based platform where we monitor the performance and operation of the system, as well as conduct different calibration efforts, which you'll hear more about later in this deck. So to think about selecting and customizing your own device, you'd first start off by determining which pollutants you're interested in monitoring for and select those appropriate gas cartridges and/or PM. Depending on how many pollutants you want to monitor simultaneously, you then would decide you either want the Air Pro or the Air Lite system. We also have multiple different probes available to monitor different meteorological events, noise, or other types of sensors that you can connect directly to the system. Then all of this is tied into the cloud software, and we also provide other data tools if you wanted to import or export data using an API. This slide lists the wide range of gas sensors and other sensors available. Right now we have 12 different gases and PM available, and there's 4 or 5 more gases set to be released early next year. Here's a closer up view of the Apex Air Pro system. So again, this system can monitor up to 5 gases plus PM simultaneously. And at the bottom, there's 4 additional connectors where you can tie in different probes or sensors. Keep in mind, these units have embedded temperature, humidity, dew point, and pressure sensors, and you can tie in your specific power requirement right here. Here's a close-up of the more compact air light system, which monitors 2 gases and PM simultaneously, and has one additional connector for a probe or supplemental sensor. This slide highlights a couple of the capabilities of the cloud software as far as visualizing data goes. So it's quite easy when you're using an anemometer combined with our unit to generate heat maps or pollution hotspots. You can also use these sensors to identify leaks. You can visualize the PM size distribution, or conduct multi-parametric analyses, or even generate customized reports that are automatically created and sent out to a particular listserv. So hopefully you're a little bit familiar with the technology now, and I'll shift gears into discussing what we do to ensure high quality data. So before getting into that, I want to just highlight some of the typical issues that sensors tend to face. So first, as I'm sure many of you are very aware, is the impact of environmental conditions. So we know that there's a nonlinear response to temperature, humidity, and pressure. We know that there's many cross sensitivities between pollutants that can lead to inaccurate sensor readings. And we're also aware that baseline and sensitivity drift are inevitable. And then furthermore, for particulate matter, the specific location and the exact type of particulate is going to impact your readings and findings. But our product, we've really considered all of these challenges up front and have designed in ways to mitigate the effect of these challenges. So much of addressing these common sensor issues takes place in the factory. So Kunek, the manufacturer, has designed this quality control, quality assurance process where much of it takes place in the factory setting. So if you follow along this graphic, what Kunek really is selective in identifying the best-in-class OEM sensors. So after they're selecting very high-end sensors, they go through a lengthy characterization process where the performance of each individual gas sensor is evaluated in an environmental test chamber where it's exposed to the full range of the temperature, humidity, and pressure conditions that the sensor is rated to perform in. Then an algorithm is designed for each specific sensor so that the correct influence of these environmental conditions is absorbed by the sensor itself. And all of this is stored on a PC board in this sensor. So next, the sensors are calibrated still in the factory setting, and their performance is tested again to ensure that the algorithm and calibration settings were appropriate. At this step, if the sensors don't pass their validation step, they're disposed of. And unfortunately, we see a pretty high rate of having to dispose of sensors, almost 50%. So this is part of the reason that these sensors are perhaps a bit more costly than some of the other commercially available sensors. So once the sensor earns its certificate of calibration, sensors are sent out to end users. And upon field deployment, users are given very specific instructions on how to properly operate and maintain their sensors. And all of this is detailed in a very well-written user manual. So finally, the operation and performance of the sensors is closely monitored by using the cloud software, and any performance degradation is communicated to the end user so they can be aware of proper timing to order replacement sensors. And most sensors last for about 2 years. Now, in these next 2 slides, I'm going to show just a couple of graphs comparing the performance of the Kunek sensors at a co-location study with different reference stations in different parts of the world. So you'll see that nearly all of these sensors have very high correlation with reference data, and that's in part thanks to these lengthy factory quality control, quality assurance steps that are put in place. Here's another slide just showing some more of the performance comparisons with reference stations. And I'll just comment here that after this webinar, we will be sharing out a recording of the webinar along with PDF of the slide deck. So another way that quality assurance is ensured is by a clever operational and maintenance feature within the cloud to trigger automatic alarms. So this is a screenshot from the cloud itself, and operators with appropriate login credentials can access these alarm logs. So email notifications can be tied to each instance where some sort of factor of performance outside of a normal range is identified in this alarm log. So the columns here correspond to the status of the alarm, if it's active, if it's been confirmed, if it's ongoing. It also identifies the specific device that's impacted and how frequently this issue is occurring. There's a description as to what's going on with this particular alarm, and there's a help column that gives you recommendations for how to fix your issue. Additionally, the extensive cloud user manual provides more detailed instructions for how to troubleshoot or address particular alarms. I've grabbed just a couple of examples of what typical alarms might include. So we're monitoring all different types of operational and performance settings for the alarm. So you might see alarms that cover communication issues. Maybe there's some sort of cellular issue in the area. Maybe there's environmental operating parameter issues, like you're out of a temperature or humidity range. Could even be that your particle sensor is partially obstructed. Maybe there's some debris stuck on the covering of the sensor. You need to go check out what's going on. Now, these alarms also give you recommendations as to when it's appropriate time to conduct a baseline calibration, or it indicates if the sensor could be broken or possibly poisoned by a high concentration reading, as well as about 25 other potential alarms that are in the user manual. All right, now shifting gears a little bit, I'll talk about some of the calibration options that are used with these air systems. So first, I'll talk about gas sensor calibration using a reference. So calibration here, we're going to refer to adjusting the sensor response based on a reference concentration, and that concentration measured by the sensor itself. So this allows for an exact uncertainty of the sensor measurement to be obtained. The calibration here can either be conducted with a more traditional co-location of the sensor to a reference station, or we can certify the calibration by using a gas cylinder connected to a mobile gas hood pictured on the right. I will note that there's no need to ever send these sensors back to the manufacturer for calibration, so that saves on time and money. So this in-field calibration using a gas hood is quite unique. To the best of my researchability, I've not been able to find any other comparable options where you can tie in this gas hood directly to the system itself. And in the field, or if you're in the laboratory, you can conduct a calibration test or a bump test. To do this, you simply attach the gas hood to the system and adjust the data reporting settings based on the gas hood calibration procedure. Then in the cloud software, you conduct first a baseline calibration or a zero calibration by flowing zero air. And then you can perform a span calibration or a sensitivity calibration by flowing the calibration gas for the appropriate amount of time and adjusting the span calibration. So when you're in the cloud and conducting a calibration, you'll see a screen similar to this, and it'll step you through exactly what to do to calibrate your system. So first, you'll identify what type of calibration you're trying to conduct, what device you're using, what sensor, specifically like what gas sensor you're trying to calibrate. Then you select your reference value and the period of time that you're trying to calibrate for or across. After that, you can preview what the calibrated data would look like and confirm that it makes logical sense before applying any changes. And then you get additional preview where it shows you the calibrated results, and you can confirm those results across the set period of time. And I also just will comment that these results, these calibration results, can be applied retroactively for a specific period of time. The other option that we offer is a gas sensor correction without a reference. So in this case, a correction is an act of adjusting the sensor response without any external reference data. The correction can be very useful for reducing error and mitigating drift, but it doesn't represent an exact uncertainty measurement. And there are two different types of corrections available to the user: baseline or a span drift correction. So for the first, the baseline drift often occurs due to variations in temperature, often when the temperature changes by more than 10 degrees Celsius or about once a season. And to account for this, you can apply knowledge and understanding of the pollutant's typical daily behavior, because there's fluctuations in expected value of pollutants depending on the time of day, and correct the baseline based on the expected value at a set time. So for example, NO2 reaches a daily minimum overnight, while ozone reaches a daily minimum typically between 5 and 8 a.m. So you would, and I'll show on the next slide how this would be applied. The other type of correction is a span drift correction. And this would typically occur due to a loss in sensitivity of the sensors. We expect to see some decrease in span accuracy between 10 and 20% over the course of the year. And automatic corrections for sensitivity are currently available for the CO2 and methane sensors, but will be available for all sensors in the near future. So to highlight what I mean by applying a baseline correction, here is a couple cycles of data, daily cycles of data for NO on the top and for ozone on the bottom. And you can see that overnight, the low point, the minimum values are being achieved overnight, and it's close to, if not at, 0 parts per billion. And so you would identify these periods as your minimum, and you could adjust your baseline to appropriately shift or offset the entire set of data. Now, finally, PM sensor performance is impacted mostly by particle type. And to calibrate the PM sensor, you apply a correction factor similar to equivalent instruments. For this, you can either co-locate the device at a reference station and collect data for 2 weeks and identify a correction factor compared to the reference station, or our PM sensors have been certified by MCerts and include an embedded correction factor. So the MCerts certification factor was developed while testing the units in a city in UK. So if you operate these PM sensors in an environment that's extremely different from UK, your correction factor might not be as accurate as it could be. So for example, if you're operating in a mining site compared to an urban setting, you might have a larger error at the mining site. For a co-location with a reference site, you would want to set up the Apex Air unit at the reference site and collect data for about 2 weeks. And you'd compare the PM data from the sensor system to the reference station and generate a regression line, and then identify the slope through the origin. This slope value is used as the correction factor and can be plugged right into the cloud software to correct the PM data. So this slide provides a bit of a summary or an overview of recommendations related to calibration and corrective maintenance. So note that all of the sensors last between 1 to 3 years, with most of the sensors being able to operate for about 2 years. We know that performance degrades over time due to natural loss in the electrochemical capabilities. And we recommend calibrating or applying a correction every time the average temperature changes by about 10 degrees Celsius. So this schedule is embedded in the user manual, so you would refer back to this as you're setting up and operating the system. Finally, I'll just call out that our products have been independently evaluated or certified by a number of different organizations. So AQ-Spec they have a couple years ago did an evaluation of the Kunec products, and just earlier this spring and summer conducted a lengthier review of multiple units, and they have released a draft of the Air Lite performance, which you can find on their website, and they should be releasing their findings for the Air Pro very soon. Air Lab out of France has also evaluated these systems for both gases and particles. We've been working through the EPA co-location with protocol metrics and plan to be releasing data in their protocol format in the near future. And then Senelec and MCERT have also evaluated these devices. So just to summarize, the Apex Air products are accurate to about 80 to 85% accuracy compared to reference stations. They're very versatile because they're a multi-pollutant system, and you can swap out different gas cartridges very easily depending on the needs of your specific project. Our PM sensors are capable of accurately measuring both fine and coarse particles. We offer perhaps the widest range of pollutants available on the market, as well as different meteorological systems that you can tie right into the unit. Our units are quite compact and can operate off solar panel or main power, and they have an internal battery that allows them to run for around 20 days without any charge. And then you just heard a lot about the different calibration, co-location, correction options that we provide. So hopefully this helped to address some uncertainties perhaps about how the Apex Air products function and what we do to maintain quality assurance and calibrate the systems. And with that, I'd encourage you all to reach out to connect with me. Love to have a meeting or discussion to hear about your upcoming projects and figure out if these systems would be a good fit.